The title of our paper is Kigumi Shelf by Date-Driven CircularSaw. First, we would like to explain a brief background. With the spreading of CNC machines, the shapes we can fabricate are becoming increasingly diverse and complex. Complex machining is possible because of the high capability of the machine without human intervention in the machining process. In general, the more complex a shape we wish to fabricate, the higher the cost. This is particularly true in the case of subtraction machining technologies such as CNC milling. The cost of the fabrication machine itself is also a factor. Advanced fabrication with robot arms is generally more expensive than using 3-axis CNC machines. This cost can be a major drawback for beginners who are interested in making things. Therefore, we have devised a relatively simple and inexpensive way to enable unskilled workers to perform complex machining by using information technology and collaboration between people and tools. As a case study, we have developed a circular saw that can process wood at a variety of angles in 3 dimensions. Using our developed fabrication machine, we built a Kigumi shelf. We will now describe the modification process of the tools and the building process of the shelf. The Kigumi shelf was fabricated on site, on north side and south side walls of a 25 square meters room at the University of Tokyo. Since the room was not large enough to accommodate large machinery or a large group of people, self-assembly of the structure with few people was essential. The shelf size is 4 meters in height and 5 meters in width. There are 94 shelf boards, 427 timbers, and 23 20 notches, all with different dimensions. Since the digitally driven machine assists us in the timber processing, there is no need to standardize the detail of the joint. To make the shelves more versatile, their edges was moved back and forth, and their height was changed. This alternation increased the space available for placing objects on the shelf boards. Because the dimension of the square timbers vary slightly according to the size and height of the shelves, the cutting positions and angles are not the same. The shelves were cut using a 2D CNC machining shortcut, while the square timbers were cut primarily using our modified circular saw. The modified circular saw was developed to allow automatic control to enable cutting at different angles. We also developed a QR code-based component management system to facilitate the management of more than 600 similar but different components. Automatic control was achieved using stepping motors that were controlled via an Arduino board. The stepper motors set the circular saw's angle and height configurations and the timber's position via 3D printed gears. The machine was modified to have numerical control in 4 mechanisms. Timber piece angle against the blade, showing red on the left. Timber piece cutting position, showing purple. Blade height, showing red on the right, and blade tilt, showing purple. During the development stage of these 4 mechanisms, various problems were found, such as insufficient rotation torque, gear disengagement, and interference with other mechanisms. After analyzing and considering the failures, the gears and bases were rebuilt and improved continuously. Here is a video of the developed circular saw being used for timber processing. In addition, the developed circular saw had limitations on the range of wood processing. The maximum length of a piece of linear timber that can be processed is 1.2 meters, and the angle at which the wood could intersect horizontally and rotate on its axis were limited to the range from 45 to 135 degrees. The construction of the Kigumi joints was parametrically studied in Grasshopper. Each joint is a division of 2 pieces of wood that intersect. The joint insertion direction can vary depending on how the intersection volume is divided. We found out that the difficulty of cutting a joint can be classified into 3 categories based on the relationship between the size and the insertion direction of each timber. The first pattern is when the insertion direction is parallel to the 2 faces of the timbers in both pieces. The second pattern is when the insertion direction is parallel to the 2 faces of only one timber piece. The third pattern happens when the insertion direction and none of the faces are parallel. These 3 patterns have different characters, including the number cut in and the insertion direction. Having the insertion direction different from the direction of gravity and other structural forces, we can make sure that the joint will stay in place. As a result of these studies, we adopted the first pattern that requires the fewest number of cuts. It allowed the highest level of flexibility of the joint angles, but still within the constraints of the machining tool. While taking account of the constraints of the machining tool, we created an algorithm that can generate a joint no matter how the 2 pieces of wood intersect with each other. The constraints of the machining tool also affected the alignment of components. Therefore, the development of the machine, the study of the joint, the study of component alignment, and their respective relationship were taken into consideration simultaneously. Due to the limited size of the components, the shelf was arranged in a triangle configuration with each component assembled in a zigzag-like pattern. To ensure that the components do not interfere with the placement of objects on the shelf boards are placed on the diamond grid, and the shelf supports are placed in the gaps between the boards. To prevent confusion during assembly due to the different dimensions of each component, each member is given a name on the model. The name and location are assigned to every component. To manage these more than 600 different components, a QR code containing processing data was created and attached to every component. By scanning this QR code and transferring the data onto Grasshopper, joint processing starts. We will now explain the procedure for machining the components. When we scan the QR code with a smartphone, the data is sent to Grasshopper. Based on the machining data related to the scanned QR code, 4 mechanisms are set to the desired values by pressing buttons in Grasshopper, as shown in the video. The timber is placed on the positioning guide, and the operator slides the screw timber to cut a section of the joint. Then, the remainder of the joint is cut off with a chisel. In the process of machining the parts, there were problems with machining accuracy and machining time. To solve these problems, the linear actuator was removed. Instead, the operator performed the marking by hand to reduce the margin of error to 1 mm or less and cut the time required to cut a single joint in half. When assembling the Kigumi shelf, the shelves were assembled without using drawings, based on the addresses in the QR code and minimal help from the 3D model. An average of 3 workers per day, a total of 22 people worked together to assemble the shelves. After these developments, fabricating the Kigumi shelf was completed. In this research, we demonstrated how non-professionals can accomplish complex processing of timber and assembling structures using digital assistance tools. The role played by digitally aided technologies in this process is to adjust various constraints about handcraft itself, such as tool, processing, and assembly constraints. Availability, cost, and technical requirements are major concerns that non-professionals encounter in most handcraft projects. This achievement shows how the collaboration between people and tools can bring out creatively designed objects when digital technology supports handcraft. Digital fabrication has enabled complex shapes through technological development. We expect that the ability of humans to easily handcraft complex shapes with the aid of information technology expands the possibilities of handcraft. Thank you for listening.